everyone. In 2020, researchers from Wildlife Conservation Research Unit at University of Oxford were facing a significant challenge. They wanted to find the total number of African elephants in savannas. Now, African elephants are critically endangered species, mainly concentrated in these grassy woodlands that take up about 20% of Earth's land area. That's 1.5 times the size of Europe. So you could imagine how challenging it would be for the scientists to find the elephants in this vast region. After considering a number of approaches, such as crewed aircraft sent to several hundreds of probable grasslands, or worse, sending a team on site, one method eventually came to the scientists' rescue: satellite imagery. The satellite that provided them with the images was orbiting at 600 kilometers above the Earth, traveling at approximately 27,000 kilometers per hour. Now you might wonder, what enables these satellites at such massive distances and speeds to take incredibly stable pictures of objects on Earth? And even before that, how does the satellite know when exactly to point the camera and where? The answer lies in a technology called Attitude Determination and Control System, or ADCS. Through this video, I will explain to you how an ADCS functions within a satellite almost entirely without human supervision on its own. Now, before diving into the details of ADCS, a quick note. Based on the end application, the satellites fall roughly into three categories: imaging, communications, and scientific exploration. So the ADCS method that I am about to explain to you now will apply to an imaging satellite. It could as well apply for communications and scientific exploration satellites. Additionally, once the spacecraft is launched into space, ADCS is used in a variety of scenarios where spacecraft's rotational motion is supposed to be controlled. One such scenario is sun acquisition, where the spacecraft is supposed to point its solar panels to the sun to recharge its batteries. Therefore, although we are discussing just one of the applications of ADCS in this video, it's important to bear in mind that others exist as well. With that said, let's define the terms attitude determination, and attitude control.
Attitude, or orientation, of a three-dimensional rigid body is its rotational state with respect to a reference frame. This rotational state can simply be a set of three angles.
A reference frame is nothing but a set of three zero lines relative to which the angles are measured. If a body is completely aligned with X, Y, and Z axis, its attitude in angles will be 0, 0, 0 degrees, meaning 0 degree around X, 0 degree around Y, and 0 degree around Z. Meanwhile, if the body looks like this, its attitude will be 90, 0, 0 degrees. When rotating a camera axis by axis, the sequence matters. For instance, rotating 30 degree around X, then 90 degree around Y, and then 30 degree around Z produces a different result than rotating 90 degree around Y, then 30 degree around X, and 30 degree around Z. This is why ADCS angles are typically referred to as Euler angles. Notice here that I am not using the terms attitude and angle interchangeably. It's because angles are just one of the many ways in which attitude is represented. There are other ways as well. More on that later when I discuss the attitude parameterization in another video. So now you get it. Attitude is simply orientation of a satellite, usually measured in the form of three angles. Now to talk about attitude determination and control, let's forget the satellite for a moment and focus on the camera of your phone. Say you're trying to take a picture of your cat. Before you click that capture button, you go through three steps unconsciously. First, you sense what is the current attitude of your cell phone. Second, you sense what is the current attitude of the cat, that would be the target attitude. And third, you align your cell phone's attitude or orientation to that of the cat's attitude or orientation, and then you go ahead and click that capture button. The key here is that you adjust your camera to minimize the difference between your phone's current attitude and the target attitude. In this process, step 1 and step 2 refer to attitude determination, and step 3 refers to attitude control. For you, a human with sophisticated cognitive and motor capabilities, this might be trivial, but for an inanimate object, tumbling in space all by itself. It is not. Now let's extend this example of a mobile to a satellite. Once the satellite enters imaging mode, after receiving a command from the ground station, it becomes mostly autonomous, unless something goes horribly wrong. In the case of imaging of African elephants, the target attitude corresponds to the land region that needs to be imaged. Then next, satellite takes the difference of its current attitude and the target attitude and then maneuvers itself to align the camera's attitude or orientation to that of the target attitude and then takes pictures. This whole process can be shown in a block diagram. First, a sensing device mounted on the satellite measures the satellite's current attitude. Second, a computer computes the difference between the current and the target attitude. And third, a mechanical device adjusts the satellite's orientation to minimize this difference. This loop is continued until the target attitude is reached and maintained. The first operation, sensing, is done by attitude sensors, such as a gyroscope, which measures the satellite's angular rate. The second operation, difference calculation, happens in the satellite's onboard computer, which also stores the target attitude sent from the ground station. The third operation, motion, is performed by an actuator which applies torque to rotate the satellite. Now let's address a crucial question here. How do we ensure that the torque created by the actuator results in the precise rotation we want? No more, no less. That's when ADCS design comes into play. Engineers tune ADCS parameters based on automatic controls engineering requirements. These requirements are, for example, angular rate, overshoot, and settling time. Physical limitations of the satellite's body also play a crucial role here. Now, tuning of ADCS is a topic that deserves its own video, and I'm definitely gonna make one. But for now, let's focus on actuators, the devices that rotate the satellites physically. Examples include reaction wheels, reaction thrusters, and magnetic torquers. These devices help to maintain a stable attitude of the satellite around the target attitude, and whenever the satellite drifts away from the target attitude due to whatever reason, such as disturbance, the actuator ensures to nudge the satellite back to the target attitude. In addition, actuators are also extensively used all the time to switch the satellite from one orientation to another. So, in addition to keeping it stable, they also create maneuvers to switch the satellite from one orientation to another. Alright, to wrap up, now you have a basic understanding of how satellites' rotational motion is controlled in space to facilitate impactful applications like saving endangered species. In the future videos, I'm gonna dive deeper into cool topics like ADCS design, post-launch stabilization, orbit change, interplanetary travel, and basically everything related to satellites and satellite engineering. So if you found this video interesting, please hit that like button and consider subscribing to my channel. Also, don't forget to let me know in the comments what topics you would like to cover next. See you in the next video.